Okay, please. So first of all, I would like to thank the organizing committee for giving me the opportunity for this presentation. And in this presentation, I will talk. The title is "Marked Biomaterials for the Therapy of Bone Tumors: Conjugation and Release of Organic Molecules from Bioactive Gases." And in this presentation, I will talk a little bit about the pH-sensitive conjugation literature, and then I will show you the first steps about our works in the conjugation of bioactive gases. So, one of the major problems in the therapy of tumors is the difficulty of developing a selective therapeutic strategy which has a major toxic effect on tumors without damaging normal cells. And with respect to the surrounding tissue, normal tissue, a tumor has a very different metabolic and nutritional environment. In fact, it has a very heterogeneous vascular distribution, which is often inadequate to supply the nutritional needs of the expanding population of cells. And this results in a lack of oxygen and many other nutrients, and as a result there is an increased aerobic and anaerobic glycolysis with the production of lactic acid, and this results in an acidification of tumor tissue. And several microelectrode measurements on both animals and human tumors agree that while in tumor tissue there is a bigger range of pH in the extracellular compartment of tumor tissue, a range between 5.8 and 7.7 pH units with an average value of 7.0. In normal tissue the range is shorter and the average value is 7.5 units. So in tumor tissue there is a more acidic pH. And osteosarcoma is the most common primary bone tumor, and its standard therapy consists of surgery as preferred means of local control, and its therapeutic protocols involve the use of cisplatin and doxorubicin. Doxorubicin is actually a wide-range anti-tumor drug, but its use in the therapy of bone tumors is still limited because due to the lack of specificity and selectivity of conventional drug delivery systems. And this results in a high dose distribution to normal tissue, and anthracyclines are known for their cardiotoxicity. So we could be able to use this altered metabolic feature of tumors, that is the acidic pH, into a useful resource if we were able to functionalize a bioactive glass with a covalent bond which can be hydrolyzed in acidic condition. In this way, we could use this bioactive glass as a prosthetic material in order to fill in the bond defects that come after tumor extirpation, and at the same time we could trigger the delivery of the drug directly at the tumor site, only in presence of the tumor, so only when its effects are needed, and with low levels of system toxicity. That is to say, we could build a pH stimuli responsive drug delivery system. And in the literature of pH-sensitive conjugation of doxorubicin, the most frequent examples of covalent bonds used for this purpose are the hydrazone bond, which involves the ketone in the tetracyclic moiety of the molecule, and the amides of alpha-beta unsaturated anhydrides, which involve the amino sugar moiety. And the amides of alpha-beta unsaturated decarboxylic acids were first reported in 1981 as pH-sensitive spacers by these researchers, and they conjugated downamycin to aminoacyl polyacrylamide beds using these two anhydrides, maleic anhydride and cis-aconitic anhydride. And the result, they studied the release at different pH, and also the cytotoxicity, and the results they got is that only cis-aconitic anhydride proved to be pH sensitive. So they explained this result because they interpreted this result in this way, that in the conjugate, the hydrolysis of the amide bond, and there was intermolecular catalysis by the free carboxyl, which is held in cis position by the double bond here, this amide bond. And the maleic derivative lacking this free carboxyl function doesn't work in the same way. But recently, it was published, this work by this Chinese group about the conjugation of doxorubicin to pullulan with maleic anhydride, and actually what they obtained in both release text and cytotoxicity tests was that there is a similar pH-sensitive behavior also with maleic anhydride, only with longer reaction times, longer release times. So this work inspired our work on the functionalization of bioactive glasses. And Gianluca Malavasi from the University of Modena synthesized a series of bioactive glasses containing aminopropyl tritoxysilane in different amounts and with different synthetic routes and different thermic treatments. And among them, the one with the best properties, most promising properties, was chosen for functionalization. And it was the one with 25% of PTS as precursor inserted in a sol gel synthesis and treated thermically at 423 Kelvin. And as you can see from the same micrographs, the glass morphology presents an heterogeneous distribution of the particle size, and with these aggregates probably made up with PTS, and EDS microanalysis confirms the presence of carbon and nitrogen coming from APTS. And acid-base titration tells us that on the surface of this glass there are 3.5 millimole of amino groups per gram. So we had this glass expressing amino groups on the surface, and the first thing we did, we reacted it with maleic anhydride. So considering the uncertainty in the literature and its simple structure and low cost, we thought it was worth considering it. We set up a very simple synthesis at room temperature with the diethylator in short reaction times, and we were able to see from the Raman spectrum the carbonyl stretching of the amide bond and also of the carboxyl group deriving from the anhydrate opening. And after this, we had to do a conjugation, but instead of doxorubicin, we chose a very simple molecule with an amino group, which is aminoethantiol or cysteamine, and we again performed the reaction in the methyl sulfoxide with short reaction times, and we were able to see an increase of the amide, of the signals of the amide, the carbonyl stretching of the amide bond. And thanks to the thiol functionality, we were also able to see the stretching of the carbon-sulfur bond, and thanks to the sulfur presence, we were able to calculate through elemental analysis the amount of cysteamine conjugated. So, as a second model molecule, we chose something more similar to doxorubicin, which was 5-aminofluorescein, because we wanted to study the release of the molecule with spectroscopic techniques. And we did the reaction again in the same way we did it for the cysteamine, and again we saw an increase of the amide signal. Then we performed the reaction also with a different synthetic pathway, because since the reaction times proved to be a limiting factor due to glass degradation, we first reacted aminofluorescein with maleic anhydride, and then we conjugated on the bioglass this product. In this way, the bioglass had to endure only one reaction step. And how much aminofluorescein did we conjugate? The results from thermogravimetric analysis were a bit surprising because we obtained a higher amount of aminofluorescein conjugated for the first way of synthesis instead respect to the second. And we obtained 65 grams per 100 grams of glass, which is indeed quite a big number. And on the release, on the conjugates from the two synthetic pathways, we performed the release test in two buffers, phosphate buffer at pH 7.4 in order to mimic the physiological pH of biological fluids, and acetate buffer at pH 4.2 in order to simulate the pH of intratumoral environment. And what we can see is that, first of all, with increasing soaking times, there is an increase of aminofluorescein released. So the system acts as a controlled delivery system. But what is more important for us is that if we compare the release in the two different pH buffers, the release at acid pH is always higher than that at physiological pH, if we consider, for instance, after 1 week. And this is consistent with the development of a pH dependent, of a pH responsive drug delivery system, which is what we want to develop. For short soaking times, actually, we have to consider that there is a high amount of aminofluorescein released in the first route from the first conjugate coming from the first synthetic pathway, also at pH 7.4, respect to the total amount of aminofluorescein released in the acidic conditions in the second pathway. And we explain this because in this first route, aminofluorescein can establish weak interactions with the silanols on the surface. And in this way, there is a certain amount of aminofluorescein which is just physisorbed on the glass. We did repeated rinsing with the polar solvents, but nevertheless, a certain amount still remains in the glass, and it is better released in pH, physiological pH, because the solubility of aminofluorescein is higher there than in acidic pH. And also, if we compare the total amount of aminofluorescein released to that loaded on the glass, the amount released is very low, that is to say, less than 1%. So in conclusion, we obtained a covalent functionalization of a bioglass containing APTS, which we characterized with Raman spectroscopy, titration, elemental analysis, thermogravimetric analysis, and UV spectroscopy. Then we did release tests, which we investigated with emission and absorption spectroscopy, and our system proved to be pH sensitive. Yes, there is a low amount of fluorescein released, but it is comparable with previous studies on the same material, and moreover, we have to keep in mind that we are going to use this, we are planning to use this material for some protheses which will release the drug directly in the tumor site, so the concentration needed will be very low. And as a future plans, we are planning to work on cis-aconitic anhydride in order to compare it to our results with the maleic anhydride. And yes, of course, it will be interesting to develop a fluorophore which is an aliphatic amine, because aminofluorescein is an aromatic amine, which changed quite a lot. And we are planning, of course, to do the conjugation with doxorubicin finally, which is our target, and also to apply this study to other hybrid materials, not only APTS containing glasses, but also titanium chitosan materials. So I want to thank Professor Marta for giving me the opportunity to work on this project, Professor Cerato, Valentina Aina, who does most of the work, my professor Will Viscardi, and the two students who worked on the project, Francesca and Walter. And of course, all of you for the kind attention.
Thank you. And now the question time. Okay, please.
Claudio, can you show one of the first slides? Next. That previous slide. Can you repeat please about the temperature for T?
Yeah.
423. What is the temperature?
It's just the synthesis of the glass.
The temperature in which the glass was synthesized. Yes.
After the synthesis, which is the synthesis happens through a Solger process. So the constituents, the components, the reactants are mixed in solution. Then the glass is made undergoes a process which is called gelation. It becomes a gel, and then it is treated after the synthesis thermically. And the person who did the synthesis was not me, but Gianluca Malavasi, tried different synthetic routes to insert the BTS and different amounts of BTS and different thermic treatments, different temperatures. And this one was the one which, this thermic treatment after synthesis, was the one which allowed us to have the highest amount of amino groups on the surface available for functionalization after.
Okay.
Yes, the question.
My question is about pH of intracellular and
Extracellular.
dependence. It depends. I mean, you showed the data only for tumor and cancer cells as to you deals with osteosarcoma, yes?
Yes.
And it connected. It depends on type of tumor. I mean, so it is.
No. These data are general for every
It is
tumor.
generally
Yes.
not
But
dependent on type of tumor.
no, and they are not related to the intracellular compartment, which is very similar in both in tumor and in normal cells, but with the extracellular compartment. The difference in pH of 0.5 units average is more in the extracellular compartment than inside.
Yes, but you give not one volume, you give
Range.
So what, in what points is this more or less, in what points of tumor, I mean?
Well, these are data coming from measurements made on all tumors, so I cannot answer specifically in detail for each tumor about which values are more, if this is your questions. These are general data. Yes, I know this one is a very big range, but these are general data collected from all tumors. So.
But it in living cell, or it is extracted from?
No,
I mean,
from
in
the
living organism or extracted?
Yes. No, in living organism.
In a living organism.
Yes.
So it's data. It is your data, or it is?
No. Literature data.
It is literature.
Yes.
Okay. So.
Reviews about the pH of tumors. There is also reference.
So, more questions? So, there is no questions. So, thank you very much for your report.